Okay, so here we're presented with a moments question, and as we read through quickly, we see we have a uniform rod of length 2 meters and mass 50 kilograms. It's held in horizontal equilibrium on two supports C and D. We're told the distance of AC and DB is an unknown distance. We're told that the reaction in the rod at D is twice the magnitude of the reaction at C. Okay, a lot of information there. Let's try and pull out the most important pieces and model it. So the uniform and these two reaction forces we need to be really careful for. Setting up the diagram and the supports C and D. I'll start with this unknown length and this center mass, and then I'll start to put on the lengths as expressions. So 0.2, 0.8, 1 minus x, and x. The reaction forces at C is R and at D is 2R. And really, I'm ready to go from here. So the same techniques as always. We're going to resolve vertically. The forces up should equal the forces down. And that gives us an expression of R, 50 over 3G. Keep this as a fraction, no need for a decimal, and no need to multiply out the value of G, the 9.8. Next, I'm going to take moments from D. So the distance to the force R is 1.8 minus x. Multiply that by R. That's my clockwise moment. The distance to the 50G is 1 minus x. That's my anti-clockwise moment, and they should be equal to each other. If I expand and simplify, trying to make x the subject, that should be enough for me to solve for x. I recommend that you keep things in terms of G. There's no need to have those large, unwieldy numbers. G's are actually good, and they might even cancel out by the time we get to the end of the question. Okay, so next we'll factorize out the x. And it's just one more step. 50G minus 1.8R all over 50G minus R. Now, we did find an expression for R earlier when we resolved vertically, and I can just substitute that in now, and then I'll be ready to punch these values into the calculator. It's an answer of 0.6. X is 0.6 meters. So if you like, we can come back up and just add that to the diagram, and we know all of those lengths. Okay, moving on to part B. Okay, in part B, the model has been changed slightly. Let's try and pull out those changes. We've been told that the support at D has now moved and is called E, and it has a distance of 0.4 meters from B. A mass has been added at the point B, and the reaction forces are now in a different relationship. It's 4 times the magnitude of the other. So let's get those supports in, and I'm gonna still have a uniform rod. So right at the center, I'll put the weight, A and B. I'm also adding a weight at B, and here's the 0.4 we were given in the question, and I'll go ahead and fill in these other lengths as before. Reaction forces, as we're told in the question, are R and 4R. Same strategy. Let's resolve vertically. So 5R equals the downwards forces, 50G plus mg. And I can get an expression for R from that. It's still got a couple of terms to it, but it's maybe going to be easier to use later on. All right, from here, let's go ahead and take moments, and we'll take moments from C. I'm clearly indicating exactly what I'm doing in my calculation. It's easy to follow. From C, we'll measure out to the middle is going to be 0.8 multiplied by 50G. I knew the middle because this was a uniform rod. The other clockwise moment comes from the mg weight, and then the anti-clockwise moment comes from the 4R. All right, we've got this expression. It's really just careful expanding of brackets and rearranging from here. So now I'm just going to substitute in that expression for R. So 5.6 multiplied by 10G and also multiplied by 0.2 mg. All right, I'm going to rearrange because I'm trying to make m the subject. So all the m terms combine to give me 0.68 mg. And making m the subject, we get an answer of m equals 23.5 kilograms, since this is a mass. All right, just a reminder, the strategy is always to resolve vertically and to take moments. As long as you had a good, strong diagram to begin with, that is the winning strategy.